Welcome everyone to day 2 of Lean for Scientists and Engineers. Today we are continuing. A reminder that our overall goal is to teach scientists and engineers the basics of logic and proofs, to introduce functional programming in Lean 4, and bring these ideas together to develop provably correct programs for scientific computing. We are on day 2 of the schedule. We're doing equalities and inequalities. And the overall schedule for today is going to start with a survey for the people attending. And so if you take a look, left my clipboard. I want to get extra information specifically from the people who are still here. And that is, here's where I left the form. Oh man, I've gotten locked out of the WebEx chat. This hasn't happened to me before. Oh, there we go. Okay. I'm just trying to paste this over. Oh, I have a link. Having the darndest time getting it posted to the chat. Here. I'm going to have my co-host send this link to everybody. Thank you. Thank you, Misbah. For some reason, I got locked out of the chat. I can't do it. Okay. Anyways, please complete this survey. It has some questions in common with the registration survey, but I want dynamic link not found. Link doesn't work. It should. I mean, maybe you failed to get it copied. Okay, I'll just try. I'll have survey of attendees. Thank you. Okay, someone found a correct one. Excellent. Let me make sure the question settings are good. Responder input should be okay. Yep, not restricted. Okay, thank you. So bottom line with this form, there's some of it's redundant. I just need to collect the same information again in case you happen to use a different email address than the one you did when you registered. But the main thing in this form I want you to talk about is, why are you taking this course? And I'd like to use Lean to, what's your motivation? And especially more ideas about above question. Some of you, it's just a brand new thing, not really sure. You don't need to fill this out immediately if you want to ruminate over this already. But maybe you're a physicist doing high energy physics and you have something you care about there. Or maybe you are a mechanical engineer. Or maybe you're, like whatever that is, I wanted to get to know you more. And I didn't have any really good free answer questions in the registration survey. But for the people who are still around and really going to focus in on this, I want to hear more from you. Okay. So we're going to next recap lecture 1. And this is, we covered a lot in lecture 1. We covered generally my ideas about doing provably scientific computing, provably correct scientific computing in lean. What do we mean by this? How can we connect science and engineering to mathematics? What does it mean to formalize mathematics with computers? What is Lean for and its math library, MathLib? Showing you some case studies that we presented in our first paper on this in chemistry, and a case study in programming that we haven't yet published on BET analysis. We're going to get more into the BET analysis later in this course. Sharing some outlook on these things, and finally, we started with getting started with Lean, getting connected with this course, Proofs About Equality. If you haven't already, I strongly encourage you to go to Zulip. It looks like this on the desktop. All right, and get involved, get connected to the Lean for Scientists and Engineers stream. This is where you'll find links to the Lean files. I won't keep sending this out by email because not everybody wants to get those, I think. Especially when I send multiple a week, for example. We'll have lecture recordings, my slides, which I'll post afterwards in case I make any changes or corrections right up until the last minute. This is also where you can create brand new topics, and you can start conversations about either things that were in the lecture or things in that form about what do I want to do with Lean in science. Okay. All right, continuing with the recap, derivations in science are math proofs. A proposition is saying that when I have premises imply some conjecture, this is me turning a derivation in science into a math proof. Theorems state that propositions are true, and proofs are going to be the step-by-step process of doing that derivation. We also explained the vision for bug-free scientific computing, that how would we compare the standard method of test-based code development to a proof-based code development approach. And there's 2 kinds of math proofs, handwritten versus formal proofs. Formal proofs allow computers to check all of their answers, and the Lean Theorem Prover is this tool that's going to be digitizing mathematics. And I mean, we're using it. Humans are digitizing the mathematics, but Lean is helping us do that. And Lean is really a game changer in connecting this to executable software and making that better too. So our vision for connecting executable code to math proofs about that executable code is that's kind of another thing we talked about. So floating point numbers, it's just really hard to write proofs about floating point numbers. But if you're limited to but we're kind of limited to only using floating point numbers for scientific computing. If we want to do proofs, we need real numbers. It's difficult to mix them, but we're developing some ways to allow us to build something interesting that sort of merges the best of both worlds here. And scilib is a vision we have for a database of verified science. My group is working on this in the field of chemistry. We especially enjoy thermodynamics and molecular simulation. But what are you working on? What are you interested in? One thing I'm going to mention as a big tip, and is that if you're trying to think about what could you do, we've been sort of realizing that if you can find software that does the thing you're doing. That if somebody has written, so like for example, we don't really work in um, classical mechanics a lot of, like, if you're thinking of big objects colliding with each other, solid bodies, so forth. We do force fields for molecular simulation. There's some sort of, but like mechanical engineers do these things. And if we wanted to formalize that part of mechanical engineering, we're going to get a lot of tips and hints by going to existing software and seeing how that works. If you think of like a computer-aided design CAD type program, if you could find that and figure out how that works under the hood, that gives you a lot of ideas about how to define the program. And if you use that as a starting point and translated that into lean, I think it's generally there's a lot of fruit to be had along that direction, rather than just saying, here's an area of science that I'm curious about. I want to write proofs about that and then maybe develop some programs to do that. Well, you're sort of doing all of the work on your own. But if you start with, there exists software where people have already figured out how to calculate things that are interesting and solve engineering problems or science problems of interest, and then you figure out how to translate that existing software into lean, that might be a little bit easier, but not necessarily the path that you need to take. Just a suggestion. Okay, and the last slide I want to bring up from last time, which is going to bridge into the next thing we're going to talk about, is the sources of errors in scientific computing software. We have syntax errors, which is not closing parentheses. And traditional interventions is you just fix that when you're writing Python or C code in your editor. It's going to flag these issues. Runtime errors are harder to catch, but you'd still catch them when you run the program, and it'll tell you where to find that error, and you can fix it after that. Semantic errors are a lot harder because the code actually doesn't produce an error message. It simply produces the results of your simulation or your calculation run, and you have to look at the results and determine whether they make sense or not. Or you have to go through the trouble of writing tests and checking things automatically to see if things are running well. We're proposing that there should be ways to bring all of these errors into the editor phase. If you're writing this with lean, we can catch the syntax, runtime, and semantic errors. So if you try missing a minus sign in your code, you just won't be able to compile the code in lean. It will be saying, this doesn't connect with the theory. You have made a mistake. And the stuff that the body of theory or the properties of these functions that you allege they should have in your theorems aren't going to hold. So you're going to catch that. You're going to root these out before you even compile the code. Floating point roundoff errors are not something we are focusing on here, but there are ways of writing tests for that. We have a really good question. And actually, I do want to pause here. This is the review point. So I do want to pause here for questions. And I got a great one from Aniruddha Saha, who is asking, why is proving things for floating point numbers harder compared to natural numbers / integers? Is it because of the limited floating point representation in digital systems? To illustrate, I'm going to go to one of my favorite little websites. It is 0.30004.com. This is a lovely website collecting the results of 0.1 plus 0.2 in different programming languages. And these are not equal. Doing this is not equal to 0. Why does this happen? Why does this happen? Well, these are floating point numbers. When you have a base 10 system like ours, again, I can't post the chat. I really wish I could access the chat. Is this working now? Okay. Keyboard shortcuts are working. Okay, but you can find the website in the chat here. Those who are joining a little bit later, there's a survey I would like you to complete. Please fill that out as well. Bottom line, there's a computing standard, IEEE 7554, that defines exactly how computers should be doing these kinds of calculations. And so you end up with all sorts of programs. You jump to C. Here is how you can show what is what is 0.1 plus 0.2. It is equal to this. Lean isn't actually on this website. Last I checked, at least. Yeah, it's not on this website. You can find it with Python, Python 2, Python 3, so forth. If you do check this in Lean, now that I'm realizing I should have made this part of lecture 2 notes. I will put this on the top. I can do 0.1 plus 0.2 greater than 3. It's not greater than 3, greater than 0.3. Do I have... Oh, Lean stopped working? Restart file. Busily processing. Come on, Lean. VS Code. My computer's a little dragging for some reason today. But if you run this, true. Because when these are defined as floating point numbers, they are floats, like your computer understands floats to be. And little math like this leads to weird round-off things. And it leads to a bunch of things that in normal mathematics is not true, is not false, is not true, is not useful, essentially. We don't want... Here, I'll be quitting my VS Code. I need this later. Okay. But that's one answer, I think, and that a lot of people wrestle with. Like, why are we going through all the trouble there? It's because floats are weird like that. We can't really prove things about floats. Nor can we compute things about reals. In some cases we can, but in other cases we can't. Okay. All right. Are there any more questions from lecture 1? All right. Then we will move right on to the second part, which is syntax and semantics. Exactly. Anthony's mentioning floats also don't have associative addition and multiplication. So simple things like the associative property, distributive property, those are really basic in a lot of that we do, and it's just kind of hard to prove anything if you don't have those. All right. Okay, my code is launching again. I'll use that later. Interval analysis. Yes. There are, yeah, I should have mentioned, for people interested in, for people in the formal method space, there are a lot of people working on doing proofs with floating point round-off error. It's just not the focus that we're taking. And it has applications in scientific computing. Okay, let's carry on. Syntax versus semantics. Here we go. In natural language, if you think of all possible combinations of words, or more generally, all possible combinations of characters. Syntax is what describes how you're allowed to combine these and order them into grammatically correct sentences. These would have rules like subject-verb agreement. I shouldn't say, I speaks to you all today, because in English, speaks doesn't go with I. He speaks is correct. He speak is incorrect. We have rules like that constrain what possible word combinations of words we're allowed to do. Reality, however, talks about what sentences are meaningful, what sentences are true. And when you select out of the sentences that are grammatically correct, we have these sentences referring to entities in real life, and they're going to be true or false, they're going to be meaningful or not, about entities in real life. So the example is, I speak to you. I refers to something out there in reality. That's me right here, and you are out there in reality too. I'm speaking to you. Semantics is about meaning. It's about bridging this space from the language to the real world. Noam Chomsky has a classic example for this. We have colorless green ideas sleep furiously. This is a sentence, and it's completely valid in terms of syntax. We have colorless green ideas. Okay, that's the subject. We have sleep, that's the verb. And we have furiously, an adverb describing sleep. You could do diagrams on this sentence, do your grammar analysis, and you'll find this, you don't break any rules with this sentence in terms of syntax. But furiously sleep ideas green colorless, okay, this one is syntactically nonsense, because now I've changed the word order and now I can't parse the grammar of this sentence anymore. I can't order it syntactically anymore. There's nothing I can, the grammar here is wrong, even though in both of these cases, the semantics are nonsense. I'm not allowed to say that some noun is colorless and green. There's a contradiction there. But also, ideas don't have color, nor do ideas sleep, nor can somebody sleep furiously. Furiously is an adverb that is not supposed to modify something like sleep. All of my conclusions about the semantics here, those are grounded in the real world somewhere. I've experienced sleeping. I have never slept furiously. People don't sleep furiously. That's just not how it works, right? Ideas themselves don't sleep. I mean, maybe you could think of some way that might work in some kind of context, but that's another thing. I just brought up the word context. And so that's another point that has to connect with semantics. The semantics do depend on context. If I said, I am speaking to you, that is only true so much that, we're in the context of this meeting right now. We're in the context of this class right now. And even the meaning of those words, I and you, those are pronouns. They refer to things in this particular context. And so on. Okay, so that's a natural language, and I think it's helpful to have some idea of what those two words, syntax and semantics, carry meanings in natural language. I'm not a linguist, and there's actually there's a massive amount of literature on syntax and semantics and language, and so many different theories about how those operate that well out of the scope. I just want to bring up this bridge between the realm of language and the realm of reality. So the next is syntax versus semantics and logic. In logic, this is similar, but it carries a slight different connotations to this stuff in natural language. So I'm bringing it up here, and these are some vocab words for people new to these ideas. If I say these are all possible combinations of logical symbols, I can only logically valid statements are going to be satisfying syntax requirements. So there's a little bit of a difference. There's a logical requirements to be satisfied here as well. Valid arguments have correct logic. Sound arguments are valid and also have true premises. So once I take a statement that's valid, if it's going to be either true or false about something in real life, that becomes a sound statement if it is also true and valid. The difference, this is again, semantics touching on reality and syntax touching on the grammar. And so here's an example I came up with. If I would write an argument, all gimbobs are woozles, all woozles are wingbats. Therefore, all gimbobs are wingbats. Okay. Even if these things don't exist, even if two of them exist, but maybe the relationship doesn't, some of these relationships don't hold, the syntax of this argument is still correct. And this is this really fundamental idea to logic and mathematics that's really elegant and something to sort of recognize that the form of a logical or a mathematical argument is universal, is absolute. That once I've established the overall structure of this argument, and we're going to get to, what is the for all character? Essentially, how do I actually write these things in logic? We'll get to that next week. When we dig into proofs with structure, we'll talk about exists, we'll talk about for all, some of these things that we have inequalities and equalities today. Those are things that scientists and engineers usually come across. We don't really come across exists and for all. We'll get to that next week. I just bring this up now. When x and y are natural, x plus y is equal to y plus x, it doesn't matter if x and y refer to anything in reality or not. It doesn't matter, about these things. Like if, and so on. So, that's where this is. But okay, I want to just emphasize a slight difference here is it's not in logic. Okay, and I want to try to make this point very clear. In logic, syntax is not only about getting your parentheses correct. It's also about getting your logical steps and your logical rules correct. And that's an important distinction because often we think of syntax and we're thinking computer languages. And if I have something like in Python and I don't close parentheses, that's what I was talking about here from a computing perspective. If I don't close parentheses, that's a syntactic error. It's also a syntactic error in logical sentences. But there's a syntax error if I'm in logic. If I write a logical statement that's not true, that's also technically a syntax error in terms of logic. Semantics is when I try to take the forms of these arguments and bring them into connection to the real world somehow. That's where we have a connection to sound arguments that are entailed by the logically valid arguments. And so I have in the slide some extra citations. You can dig into these deeper. There's further details on syntax logic on Wikipedia that will help orient you on these things. And we talk conclusions and outlook of our paper has some more discussion in a paragraph there, which I'll probably bring up right after this. I also have a link to some lectures on first order logic from Percy Liang at Stanford. These are really helpful, I think, but they're he has explained them, I think, better than I, having gone a bit further into depth. That will is also a little bit outside the scope of what I'm trying to cover because it takes some time to get through and learn and understand. But I think really helpful perspective on a computer science and AI version of understanding syntax and semantics. Okay, the last thing I want to bring up is here's sort of my proposal. Essentially, this is not exactly canonical, but this is sort of how I think of syntax and semantics in scientific computing. And in theory versus science in general, this is my first mock-up of this slide. The idea is that we have all possible combinations of symbols, mathematics, just to turn syntax into logic valid statements. And this is going to be just in the realm of pure math. So we start with the foundation of pure math, and then we start saying, among all of the possible valid statements that I've made, I'm going to step into a scientific model about the world, a theory, um, and talk about a symbolic model. And we now have entities in my theory. If we're talking about Newton's equations of motion, we would have the force due to gravity. His force equals mass times acceleration. These would be little equations that exist in scientific models. And those are math expressions, but they have meaning to them now. Force is equal to mass times acceleration. Force is a thing. Mass is a thing. Acceleration is a thing. If I have two planets interacting, they're planets. They mean something. And mass, for example, can never have a negative value. And that's something that if I was just saying, I'm going to talk about real numbers. If I'm talking about real numbers, well, this is syntax. Real numbers are pure math. They don't exist out in the real world. I have moved from the pure math world to something with mass, and now there's a constraint on there. And if I'm missing that constraint and I suddenly start talking about negative masses, well, now that's weird. And negative masses should exist or should not exist inside my scientific model. Okay. Then there's a bridge from scientific models to computable models. And what do I mean by a computable model? It means I'm able to pass some numbers into my symbolic model and I can get computations out of it. And I don't quite have time live. I just thought of a much better way to illustrate. I thought of a much better way to illustrate than I have on the slide, but a big example is Newton's equations of motion. I'll say in words. In the revised slides, I will spend some time coming up with some concrete equations. But in Newton's equations of motion, we have force is equal to mass times acceleration. And acceleration is related to velocity. Velocity is related to position. And people do calculations about how objects move through space. You can't integrate the equations of motion for arbitrary sets of equations. You can differentiate them. That doesn't really end up being much of an issue, but integration is much harder. And so people come up with numerical approximations. And you take a little small time step and you jump from one thing to the next. We had a question yesterday about finite element methods, and that's all very relevant to this, of using these approximate methods of computation to say, now I have a series of calculations that my computer can perform in order to check whether my symbolic model is going to be, and to get answers out of it, to get numbers out of this. The question would be, maybe I have a model of where the planets of the solar system should be moving tomorrow and the next day and the next year, and how should that affect our observations here on Earth? And that's where this ultimately connects to realistic models, because we make observations. And I have numbers in my observations. I went and I took my telescope and I said, okay, it is here. And I measured the results of where it is. So we have a question where, why don't I have an arrow from symbolic models to realistic models? And I thought about including one, but I just kind of left that off, because I think in the vast majority of cases, there's a much, much bigger, fatter arrow, if you would, between computable models and realistic models. The space of models that you can actually do something practical with in the symbolic models realm is really, really small, because most interesting models are complicated ones. I can do computations if my symbolic model only requires natural numbers, for example, only the counting numbers. If I have some scientific model that only uses that, then I can do calculations on that. But if I need to start invoking calculus, square roots, like there's all sorts of, like, we have squares, those show up in Newton's equations of motion, but then if I'm going to invert that, then I end up with bridging that. And so another helpful clarifying question What exactly does true or false about entities in the model mean? Let me try to answer that. I sort of have some illustrations in the lean examples we'll be getting to next. Let's say I have oh no, a triangle is a bad example. So Newton's equation of motion is force equals mass times acceleration. If I would say, well, no, I will say this is a really good question. Um, and I should also add, when I say true or false about entities in real life, true and false are kind of hard numbers, like that's 0 and 1. I can also mean degrees of truth. There's definitely huge amounts of relevance of talking about approximation and accuracy. So anybody doing an experimental science, you should do replicates and you should measure things multiple times. So bridging across this gap is not always a hard yes or no. Sometimes it's a, oh, maybe. I mean, we do this all the time. I'll simulate some molecule and I'll say, well, my simulated model of water said the vapor pressure at 273 Kelvin. Is that right? No, at 370 Kelvin is 1 atmosphere. So this is the boiling point of water. If my simulated answer comes out at 1.1 atmospheres, well, now I have a false. My model doesn't agree with reality. But if I'm comparing two models and one of them is 1.1 and one of them is 7, okay, I like the one that's just off by 10%, quite a lot more than the one's that's off by 700%. And ooh, and Martin is actually bringing up a really good point in the comment. Non-computable models can be predictive. You can still test whether propositions that are proved hold in the real world, even if you cannot decide them algorithmically. That's actually a really good point. I can, if I'm constructing my possible symbols as propositional statements, something that is logical in context, like if I'm going to say all I'm trying to come up with an example on the fly. Well, I guess okay. So a fun one is all swans are no. All swans are white is actually deviating from that. But existence of winning strategies in combinatorial games is a suggestion that Martin is raising. I'm trying to decide if combinatorial games themselves exist all the way up in the pure math space or not. Games are kind of interesting to think about because we sort of construct games. Yes, we do construct them in reality. But we are constructing games themselves as a mathematical thing. The reality I'm sort of talking about here tends to be the natural reality. So you would have to bridge this semantic gap from the reality of the world to like if I wanted to say, maybe the predator-prey relationship in some ecosystem is a game. And I wanted to, I would have to be abstracting this real system into the realm of logic. And this is the point I should have wrapped up about, I'm answering questions before I wrapped up this overall slide, is bridging from pure math to a scientific model is itself making a step semantically, because now I'm adding content about meaning to things that exist in pure math. So that's actually a little bit like bridging the syntax semantics gap in logic. I'm also doing a different semantic gap as I go from scientific models to reality. I do molecular simulations and I talk to chemical engineers who do experiments, and they are asking, is your model real? Is the thing that you've built in the computer an actual meaningful representation of the real world? Because I care about real water. I don't care about the water described by the force field, for example. So those are two different kinds of semantic gaps. And I wanted to bring both of those up because I think bridging the pure math to scientific model semantic gap is something that's a lot easier for us to tackle in terms of correcting these, bringing these into Lean, because we can define scientific models as code in Lean. Okay, it's a lot harder to define external reality in Lean and then write proofs about external reality. So there's actually, when we get to functional programming, we'll talk about input output. And that is something that takes special care and consideration about how do you handle that in proofs about input and output. And that's essentially how I perceive us bridging the realm of either pure math to reality or scientific models to reality, is you have to at some point cut through an input output loop. Or you implicitly have this because a human is writing code. You're the defining numbers that are supposed to represent reality in their Lean code. And we'll talk about those things later when we get into other things. But that's some conversation about syntax and semantics that we didn't have time for last time, but I think is really important and really unique when it comes to applying formal methods in theorem-proving languages to science and engineering. Is something that needs more time for people to reflect on and think about. All right, and so now we move on to proofs about equality and inequality. So this is a slide from lecture 1. We are going to take a short break and do intermission after this, but we'll be digging into Lean and calculation style proofs. So I'm hopping over to the intermission, and I'm not doing a song this time, so we can actually just chat if people have more thoughts. But go ahead, stretch, take a break. We will come back in a little bit to some Lean problems. So Lean lecture 2 is going to be in if you don't have a copy of Lean 2, check your email or go to the Zulip channel to find it there. And by the way, I restarted VS Code, and sure enough, now I'm getting a true. If you put the cursor over the 0.1, you can see that this has float type. It sorted that out, and I have float type. And is it greater than 0.3? Yes, it is. It should be equal to that, but it is not. It is greater than. All right. Yep, so here's a problem that we talked about last time. A plane flies 450 miles with the wind, and it takes 3 hours. Against the wind, it takes 5 hours. Prove that the plane's speed in still air will be 120 miles per hour. So if we set this up with distance is velocity times time, and we have the velocity of the plane with the wind is x plus y, and against the wind is x minus y, then how can we solve this problem? And here is what we showed last time. Here's a little problem for an illustration of that. We have in e okay. And so something I didn't mention last time that I just want to make explicit for those who are new to Lean. Example starts a proof problem. You can also type theorem and give it a name. This could be theorem plain problem. Okay, it's equivalent to do this. But the word theorem kind of carries a lot more meaning, and I would generally reserve it for things that are theorems. There's another word, you could call it lemma, which is like a theorem. It means the same thing as theorem, but it means something that's less important. Of the time, we'll try to call these things just example because we're not doing big grand things in these example problems. We're simply setting up little problems to solve connected to science and engineering. The sorry command I put in here, but I didn't actually talk about. The sorry tactic closes the goal. You use sorry to prevent Lean from throwing these kinds of errors and saying, I have unsolved goals. It turns that error into a warning. It tells the way I've seen it described is you are apologizing to Lean that, sorry, I have not yet provided a proof of this statement yet. You can use these sorries so you can sketch out something and you can fill them in later if you need to figure out which tactics to do. So the problem we showed in class is using, how do we solve this problem? So I'm going to, instead of using the dubious process of equation elimination that the YouTube video showed, we had a more rigorous way to do this. And you start by saying x is equal to x minus y, x plus y divided by 2. And you need to prove that this particular statement in isolation is true. You then do a colon equals and provide the justification for this. And ring is a tactic that is useful for algebraic rearrangement. If I then turn this expression into 90 plus 50 over 2, what I'm doing is I'm taking h1, I'm taking the x plus y here, and I'm replacing it with the 150. I'm taking the x plus y here, the x minus y, and I'm replacing it with the 90. So it's going to, how do I do this? I prove that this is true. So notice, so a thing to not think, this underscore refers to the previous statement. This one here, the right-hand side of the previous statement, it does not refer to the left-hand side of the previous statement. So the way to interpret this as the second line here is a standalone thing, and I'm going to prove this by showing x minus y plus x plus y over 2 is equal to this thing. How do I prove it? I use rewrite. Rewrite is substitution. And then finally, we have underscore is equal to 20. And how do I prove this? Well, I am proving this by, so ring is a tactic that accomplishes this, but Kevin Buzzard pointed out that there's a better way to do this. Norm num is for sorting, is for normalizing numerical expressions. This is a better, more correct tactic to do because ring is more powerful. It's going to spend more effort, computational effort closing this goal, even though it's still an easy one. Norm num is going to do it more efficiently. It's going to be more focused on doing that. So that's one little change suggested by the Lean experts to clean up this Lean 2 file. Yes, the messages get saved in the recording. We have a question. So the chat messages are saved and you have access when you access the WebEx link to that. I'm eventually going to process this and put it into YouTube, and the messages won't be on there. They should just have the actual recording itself. Okay, so this is an example there, and oh, okay. And now is the time that I wanted to bring in the question, the answer to that question about syntax and semantics. I'm going to bring up that slide. What does it mean to bridge something from pure math into something in a scientific model? What does it mean, true or false, about entities in the model? Right here, I have a mental model of some plane and some wind. I have a scientific model. This is an equation describing the situation. I have distance is velocity times time, and I have a way of describing x. X in my math, so my example in lean here, I have this entity x. X is a real number. I have this entity y. Y is a real number. I have this hypothesis, H1. I missed something in my slides. This is so important. I'm going to bring it up right now. So important term. So I'm going to give this its own slide. Hypothesis in math versus science. Okay. Those of you new to this, and my group really struggled a lot for a long time. The mathematics call hypothesis something different, and they use this word hypothesize, or the hypothesis, in a different way than in science. In science, this is what this is part of the scientific method. The scientific method says, make hypothesis, do experiment, get observations. Wow. And so forth. Hypothesis is I hypothesize that something is going to happen, and then it's not something I'm sure about. I will say, you attempt to refute the hypothesis. The science as falsification perspective that you may have heard of. Math uses the word hypothesis like assumption. Or I like the word premise because premise is, it's something that you take in your argument. Assuming this to be true for the time being, I'm going to hypothesize that this is going to be true, and then I'm going to prove it. So there's a different bit of language, and for a while I tried to think, like, is there a way, should I try to get the lean community to use the word premise or the word assumption in their thing? And no, that's not going to happen. The mathematicians are going to keep using the word hypothesis. So if you're trying as a scientist or engineer to get into the world of formal methods and the world of mathematics and lean, then learn to use and think about the word hypothesis in this mathy sort of way. It means hypothesis. And that's actually why, when I come back to here, these are denoted H1. When I started writing proofs with lean for myself for the first time, I was like, well, I can name these whatever I want. I would call them assumption one. I would like to name this A1, but the lean always calls these H1. This is hypothesis one. This is hypothesis two. And then I have my conjecture that follows. So. All right, so that's up here, so we can navigate the rest of this a little bit better. I have a hypothesis that x plus y times 3 is equal to 450. This is a statement in syntax because it's only mathematics. Oh, I'll get. I'll into that. Okay. If I want to say that x is the speed of a plane, well, now I have conferred meaning on this. I've given semantics to this x. If I want to say y is the speed of the wind, I've given semantics to y. If I want to say this whole claim, H1, is true, I'm saying there is a semantic context. There is some world, essentially, in which the plane flew this amount of time, and it was the same plane. So that's kind of what I mean when I say, um, are we going to bridge the pure math and a scientific model? Is I'm going to say that if I make a semantic error here, if I make a mistake in bridging from math to the scientific model, I have now confused. And like a way to do that is here. Let me illustrate. So a way to make that mistake is for me to write x plus 2 times y is equal to 3. What I've just done is I've made something that is syntactically correct. This is a theorem statement in mathematics that's just fine. No mathematician's going to say you have a problem with this. I would need a new proof because I changed the numbers here, but this is going to be a fine. Oh, I need to change the number too because the number won't work out. It's not going to be 120 anymore. But if I had that number in hand, I would have something that's fine in the world of math. But now there's a mistake, an error that has been made semantically. That no, when I have a plane flying with the wind, I don't double the speed of the wind and then add it to the speed of the plane. I should just take the speed of the wind singly. So this is a mistake that if we're able to define a broader system of rules that says this is how velocities of planes and winds should in general interact with each other, then we will to catch those kinds of errors. But if we have a gap there, that's a semantic error specifically. So I hope that helps. And it's a little easier to show when we're actually looking at lean code. Okay. Getting back to learning to solve problems using calculation-based proofs. One more comment. Okay, and so we're going to do another problem. And so here is, and here's another comment that I have, so a suggestion for you if you're new to lean, if you're trying to practice these proofs. Think of a proof like a maze. You have many possible paths to take, and some of these paths will make you progress toward the goal, toward the no goals, I should say, toward finding no goals left, and others lead to dead ends. The below examples here that I'm showing, these show completed solutions. Okay, this is essentially a solve, but I've filled in these sorries. We're supposed to justify the steps along the way. We're not necessarily trying to find the way on our own by proving that the given solution is correct. We'll have some of those problems later. That's the more general case. Usually you don't have it sketched out for you, but it's in the book Mechanics of Proof, that's a useful approach that it's presented. So here is another problem. A resistor has a resistance of 4 ohms and a current of 3 amps flows through it. Prove that the voltage across the resistor is 12 volts. So I have 3 real numbers. V, I, R are real numbers, and then I have 3 hypotheses. I is 3, R is 4, and the voltage, V is equal to I times R, is another or hypothesis, if you would. And now I'm going to say prove that V is equal to 12 from this. So I've set up a calc block here, and we need to fill in these sorries. If you're an expert in lean, this won't be hard at all. If you're new to this, though, you have to think of the tactics that we've been using and we've been learning. And I'm going to scroll up and remind you that here is a tactic that can do algebraic rearrangement. The RW tactic is for substitution, and the norm num tactic is for numerical simplification. So you can type into the chat who has a solution for this first sorry. I've got rewrite bracket H3. That's right. Rewrite H3. We're doing good so far. No underlines, no issues. Okay. This one is also curious because I'm starting a statement. It's also possible in this case to simply write H3 because H3 exists as the whole hypothesis and you can start from that point. You might end up having problems that allow you to do this, but other times you'll need the by and then you use a tactic rewrite H3. How about for the next sorry? Rewrite H1. Gonzalo's got this. We're good. The next one. Rewrite H2. And the last one. How do we prove that 3 times 4? We can use ring. Sure. We can use ring. This closes the goal and we're good. We get no goals at the end of this. Kevin Buzzard pointed out to me that norm num is actually a more appropriate tactic to use to close goals of this kind because it's simply doing numerical simplification. You can use ring. You'll close the goals. It'll work just fine. But when you only need numerical simplification, you don't need to do stuff with algebraic rearrangement, then norm num is going to be more efficient because it's a more appropriate tactic for that. Yep. And so I'm going to actually show. Ooh, I know how to do this. Okay. Yep. Kevin told me probably what's happening is that ring will do a bunch of pre-processing, realize that there are no variables, then just run norm num anyways. Okay. Ring is specifically for equations that have variables in them. So that's a helpful thing and a useful comment for developing better proofs. Okay, so we have a couple more, and these are harder problems. These come from mechanics of proof. We have example 1.2.1 and 1.2.3. How do we do these? This example, and I was going to try to populate these with more examples from science and engineering, but before class, I didn't quite have time to sort all of that out. So we have some pure math examples that do a really good job of challenging you to think about the different ways tactics work and the different math problems that we are trying to solve. So, how would I? Okay, so to state the problem, we have H1 is A minus B equals 4, and A times B is equal to 1, and I want to prove that A plus B squared is equal to 20. How do I go about doing that? Just to give a little bit of grounding, this is right here from the Mechanics of Proof textbook. And if this stuff is new to you, I strongly recommend doing a lot more of these problems in Mechanics of Proof. And so here, The step-by-step process is turning a plus b squared into a minus b squared plus 4ab, and using this to do substitutions of 4 squared plus 4 times 1, and then simplifying that to get 20. So, class, do we have any suggestions on how to fill in this? Sorry. Okay, we've got ring suggestions. It works. I gave you a big hint by putting a comment here. Okay, you normally, well, you don't have these comments, but yeah, this is an algebraic rearrangement, and ring is able to close this goal. How about this one? Yes, rewrite H1 comma H2. You can do these, you can compose multiple rewrites together, pass multiple hypotheses in. Okay, and how do I simplify 4 squared plus 4 times 1 equal to 20? Norm num. Great. You're getting the hang of this. This is a numerical simplification. All right, and then so we also have example 1.2.2 from mechanics of proof. This one says, assuming s is equal to 3 and r plus 2 times s is equal to -1, prove that r is equal to -7. How do we do this one? How do we fill in the right? We've got another suggestion of ring. All right. Thank you, Gonzalo. How about this next one? I want to take a minute to just remind that so when we go from this line to the next one, I'm saying, how do I show that r plus 2 times s minus 2 times s is equal to -1 minus 2 times s? That's right. You're getting the hang of it. Hey, thanks, Anthony, for chiming in. Rewrite H2. Like, so how does this work? Yes, you can see the pattern. We're switching out. We have a hypothesis, r plus 2 times s, and we're going to replace it with -1. That's how we do that. Great. I'm just going to change this back into the underline here. So how do we do the next one? Rewrite H1. Great. Thank you. And the last one? Norm num. Excellent. Okay. So now we have another goal. And so this is of the pattern. Oh, we have one more like these. And Misbah is asking, would ring work as well, or is that incorrect syntax-wise? Let's try it. That's a great thing. You can always try stuff with lean. And the thing is, it is not incorrect syntax because it does close the goal. But as I was giving in that explanation from Kevin Buzzard, if we're putting ring in here, ring is for variables. And there are no variables in this. There is no x, y, nothing like that. So it's probably going to say, I have no variables in here. I'm just going to run norm num. And that's overkill, essentially. We don't need to use ring for this. It works. But if you have a really, really long problem, it's potentially something, there's a stylistic improvement to be using tactics that are more focused on what you should be doing. Okay, so I have this comment. Algebraic rearrangement can be accomplished with tactics like simp, ring, linearith, norm num. I really should change this comment. That's not good advice. You shouldn't be using, you can't actually use norm num to do algebraic rearrangement if you have variables in there. And these tactics do different things, and you will get a better experience of how they work by either reading the documentation on them, by asking people on Zulip, and also just by trying them out. I think as a novice learning to write proofs, you'll have a goal that you're sitting down looking at, and you'll start trying things. And I think it's okay for you to just try stuff and figure out if things work. Um, it is better to understand how these techniques work and what they're doing. That will help you focus your attention and write better kinds of proofs in the end as well. But sometimes you're just trying to solve the problem. And the nice thing about Lean is, even if it's not the optimal solution, it will tell you whether or not your solution is right. Okay, we have one more. And this one's a messy one because you can see these equations are pretty long. This one is 1.2.3. Here we go. There's no answer in the book, by the way, for this one. So it's up to y'all to figure out how to fill in these sorries. Ring for the first one. Great. This one is just saying that 2 times a times n plus b times m is equal to all of this. And part of the nice thing, yeah, so the next thing we have, okay, great. Lots of good suggestions coming through. Rewrite h1, h2, and then finally, the norm num is a suggestion that works. We have no goals. Okay. Now this is where it starts to get really challenging, and I'm going to tell you in advance, coming up with the very first step of the proof in these calc-based proofs is hard. You will do better if you practice, and that's what I really recommend, is practicing. So the Mechanics of Proof textbook has a whole bunch of problems you can work through, and encourage you to do those. Here is one, and so we can be a little more focused on our time, is I'm going to do this myself and talk through how I think about colon equals, all right, calc, okay. So I'm looking at, we have hypothesis 1, A times D equals B times C, and I have hypothesis 2, C times F is equal to D times E. So lots of variables, 6 of them, I think, yeah. And we are going to try to prove that D times A times F minus B times E is equal to 0. So a big question is, how do you start a calc block? That's one of the biggest things. Like here, we haven't needed to start any, we're just filling in tactics. So to start a calc block, I'm going to start with the left-hand side of the thing I am trying to prove. And I need this to equal something. Killer case, I need this to equal something that contains things in my above hypotheses that I can use to do substitutions later. So you need to think in advance of what might you be doing in the future. So I need to do things like, can I get an A times D together? Can I get a C times F together? Can I get a B times C together? Things like that. So I can tell with this that, well, I can get an A and a D together if I just, let's put them together. A times D, I'm going to move the D into this A times F thing. So I'm going to put A and D together, and then I'm going to multiply it by F. Now I'm going to subtract it by, well, see, I could do D times B times E. But this is going to lead to problems later when I try to do the substitution, because I want to get the D and the E together. So instead I could put, well, how about I put the B up front and I put the D and the E together. Now I've written a statement that I'm, okay, I believe this is to be true. Did I write it correctly? Let me say, so I did an algebraic rearrangement. Did I close the goal? All right, I did. I got no goals so far, but I haven't yet closed my proof. That's the meaning of the error message here, is the right-hand side of my calc block is not yet equal to 0, and I need this to be equal to 0 in the end to finish my proof. So I'm going to continue, and the next thing I want to do with this is I want to take my right-hand side, and I want to replace it with the b times c over here. And so the d times e here, I can go and replace the d times e with a c times f. Now I've done some replacements. So here, I'm going to put these in parentheses to make it easy to find where those replacements happened. So this is going to be a rewrite, h1, h2. And then finally, b times c times f minus b times c times equal to 0. I should be able to cancel this all out by using ring. So this is how we close the goals. And I hope that me walking through that with talking of how do you find things, because I think writing down the statement the first time is hard. The very first one is, I refer to this as a maze. Okay, if you start going off in the wrong direction, then you can get trapped and you'll need to back up and try again. That's completely fine. We were building problems for class with science and engineering examples, and we would find we'd sometimes run into that and have to figure out different ways of doing it. Okay, so next we're going to move on to the second part of mechanics of proof. And so in general, if you're feeling rusty about this, I highly encourage you to open up mechanics of proof and go and find, so we went through 1.2 to 1.4. So you can go to 1.3 and you can find 11 examples in lean code, and you can go and try them yourself. And if you do all of them, okay, you will learn a ton and you will get more practiced at this. My student Colin Jones, who came up with the solution to this example, he wrote down how to write the solution. And I asked, well, where did you come up with this? How did you come up with this? And he said, haha, I had just done a whole bunch of mechanics of proof problems. And so like the more you practice with these, the better you'll get at writing proofs and solving these problems. All right. So now inequalities. Inequalities are a big reason we are trying to use a technique which is not usually taught in high school algebra, building a single chain of expressions connecting the right-hand side with the left-hand side with the right. That is a strategy that allows us to be more rigorous in our proofs and becomes a lot more apparent and more useful when we're dealing with inequalities. So first, a comment. A better way that I should have written this would have been to define all of these variables in the first place. Sometimes this will compile just fine, depending on the way you have lean set up. There's different automatic ways of declaring and bringing decisions in. This is a tip from Kevin Buzzard that we ought to be setting it up this way. And this is going to be a safer way to, the way he says, minimize the chances that things will have problems. Okay. So here's a case where we have, and what I should have done is I should have indented over the calc block. To have a more consistent style with the previous one. Here we have a toy mouse, and it is accelerating. It's changing its speed from 2 to 0. It's coming to a stop really quickly. Okay, it hit a wall, right? A really soft wall, I guess. It decelerated slowly. Its mass is estimated to be around 0.1 kilograms. This toy can only handle 2 newtons of force, otherwise it's going to break. Prove that the force it experiences is below this limit. Isn't that fun? We got an inequality. So we need to set up all of our equations. This is an equation defining acceleration. Acceleration is the initial velocity minus the final velocity minus the initial velocity divided by the time. And we have the force is the mass of this object times its acceleration. And we need to prove, we have colon, that this force is going to be less than 2. So how do we do this proof? So first, we bring in force is equal to mass times acceleration. Why do we do this? Okay, I want to, this is another big tip. Why do we start with this line? We start with this line because the final conjecture we have is about F. So we're going to start with something that is most likely going to lead us in a good direction. I could start with A is equal to this, but now I have A is equal to something else, and I'm not going to be able to that sort of conclusion with my final goal, which is about F. So do I have a tactic to close this first goal? Yes, we need H6. Ooh, we have 2 good suggestions. Yes, we can do this with either just defining H6 directly. We can also do by rewrite H6. How about the next one? Rewrite H5. Yep. We cannot do just H5. H5 doesn't work. We're not introducing the proposition in the first place. We will need by rewrite H5. And the next one? This one involves a lot of steps. I'm turning the M and the V1 and the V2, excuse me, the M, the V1, the V0, and the T. Yes. Rewrite H1, H2, H3, and H4 will do the job. And we have another suggestion. H3, H2, H1, and H4. Both of these work. It doesn't matter in which order you do it in this case. Because, so if I put my parentheses right here, if I put my cursor right after this one, you can see that now I've done the replacement of M, and I still have H2, H1, and H. So when I move on to do H2, it still can do it because the thing I'm looking for in H2, V1, still exists in this case. So it doesn't matter in this case in which order that I enter these hypotheses. This one's a little cleaner since they go in order, but it doesn't matter. Both of those close the goal. The last one is norm num. That's right. And norm num handle inequalities as well. We have just a bunch of numbers. It can handle the inequality relationship as well. So I think this is the part where it's starting to get, you could maybe solve something where you don't have to do all of the calculations yourself. Now here, Lean is actually crunching these together, doing this multiplication and comparing it to -2. Alternatively, you could calculate what all of these should be. So like this is another way to do it, is I could say this is equal to -0.1. See, I could do it this way, right? Because I could step it out gradually, so to speak. But I don't need to, because norm num handles this goal all at once. I don't necessarily need to add this extra line in here. It makes it a little easier to read if you were new to proofs, but this one is more concise. Okay. So we have a really good question, and I wanted to wait till we wrap this problem up before addressing it. Why is v0 equal to 2 and v1 equal to 0? Why are these called hypotheses? Or all of these? They say, I'm looking at this, I only necessarily see H6 as the hypothesis we're testing. The rest are just values being assigned. And the challenge of that language is saying, I am testing a hypothesis H6. Only H6 here is the hypothesis we are testing. We're not actually doing that. How to put it? I'm going to come back to this language. Math uses the word hypothesis like assumption or praise or premise. I got this explanation from a mathematician. The purpose of the proof is to obtain evidence to support your hypothesis. In a sense, like so the reason you do your proof, and I mean this ends up being really strong proof. It's not quite like I mean this ends up being really, really strong evidence, essentially, but like everything that follows the conversation here, all of this, everything here following my problem statement is me saying, look, you should believe that what I have stated is true. And well, no, I'm mixing things up a little bit because hypotheses, these are on the left-hand side. On the right-hand side of this is the conjecture, is the thing that I am stating. The overall statement here is these hypotheses, these imply this conjecture. I can conclude f is less than or equal to 2 after I have hypothesized or assumed all of these other things. These are still called, even though I'm just assigning a variable here, I do need to do that in the context of this example, because if I don't do that, then it's not going to be possible for me to let me delete one of these. Okay. I've broken my proof. This step is not true anymore. And no, I can't prove this anymore because I don't know what v0 is. So hopefully that helps. It takes some time, I think, and some exposure, I think, to get a little bit more used to considering the word hypothesis mathematical sense when you're used to thinking of it in a scientific sense. They're really just not used in the same way. And I'm going to kind of delete this because it's not too super related to what we're trying to do. Yep. And saying, given all these things, given H1 to H6, is this true? That is really good point. And Simon Beaumont is saying these are really propositions. Yes, they are. These are let me try accessing the info view. I'm going to catch the info view right here. Can I get the type of a? Yes, yes. So okay, here's the thing. If I put my hover over the equals sign, you will see the compound expression v0 equals 2 has type prop. PROP. That is proposition. That is the type proposition. So really that is what they are. This is how you can kind of look that up. You can access it in the info view and see that. I think I can maybe get, do I get it on the equal sign? I also get it on this equal sign too. All right. Same with the f is less than or equal to less than 2. I mean, the f is less than 2 is also a proposition. And so I'm saying we have 6 things, 6 propositions imply this other proposition. All right, so next, we have 23 minutes. Here we're going to do the exercise 1.4.1 for mechanics of proof. This one is introducing a new tactic, rel. This one is for relational substitution that allows us to do substitution, not across equality statements, but inequality statements. The example is hx is equal to x plus 3 is less than or equal to 2, and hy is y plus 2 times 3 is greater than or equal to 3. Assuming both of these propositions, both of these inequality statements, can I prove that y must be greater than 3? So we're going to start with walking you through a solved solution. We're going to start with y is equal to y plus 2 times x minus 2 times x. This is a little trick. You'll come across this. If I'm trying to prove y is equal to certain things, sometimes you can add and then subtract something, and it's trivially equal to the thing that you were starting with, and you can show that's true by using algebraic rearrangement. In this case, we want to do 2 times x because it helps us set up a substitution. We have 2 times x in this hy hypothesis. We have set that up. So now in this second step, I can say that this, and again, what the underscore does, I'm going to paste it here to make it explicit. What the underscore does is it links the right-hand side of the above line with the left-hand side of the below line. And I can use relational substitution to substitute y plus 2 times x is greater than or equal to 3. I'm taking the y plus 2 times x over here, and I'm replacing it with the 3. So I end up with 3 minus 2 times x. Then we do a rearrangement. So I'm switching here from a greater than to an equals. Why am I doing that? Because I'm trying to simplify the right-hand side here. 3 minus 2 times x is equal to this. This is a standalone statement. I can prove that with algebraic simplification. Why am I doing it this way? Because I'm trying to create an x plus 3 term that I'm going to then use in my subsequent simplification. I only had 2 times x before. Now I'm going to put x in parentheses, x plus 3 here. This creates a 9 showing up on the outside, and we can do ring to close this goal. Now I'm going to do another relational simplification. I'm going to take the x plus 3 here, and you can see the x plus 3 is being replaced with a 2. So that's what rel hx is doing. And now I can just do norm num. If you do the math, so 9 minus 2 times 2 is 9 minus 4. So this is equal to 5, and 5 is greater than 3. Okay, and then norm num is able to solve this last inequality. So there's walking you through a solution. You can see a lot more discussion of this in chapter 1.4, Mechanics of Proof. I note that you can just drop linearith is one of Lean's tactics. It can prove this all in one shot. You don't need to do this whole calc block. Um, and you can even do a I'll leave it at that. So when you're working through problems, you can do them slowly. You can also do them quickly sometimes. It depends on whether a powerful tactic exists for those. The simpler tactics are generally preferred, but sometimes it's more helpful to learn for you to walk through things step by step. Okay. Then, um, with the last minutes we have, um, how do we think about going through this problem? Do we have any suggestions on filling in this first sorry? Ring. All right. Working good. All right. How about this next one? Rel H1. Exactly. We're replacing well, let's put it in first. Rel H1. Oh, that one didn't work actually. Ah, yes, because we're doing multiple at once. There we go. And the last one, norm num. Oh, it's not working. Yes. So, and this is the point. Why doesn't it work? Anybody have an idea? Why doesn't norm num work? The people suggesting ring works. Why doesn't norm num work in this case? Yes, variables. S is a variable. So, great. We're following along, learning a lot. Wonderful. We need to take this S and cancel it with this S so that we end up having only 3 in the end. Okay. Here's another one. This one we have no roadmap. So we need to prove that x plus y is less than 2. And I'm not going to give the roadmap for this one in this case. Linearith should do it too, I think. Linearith? Yep, Linearith solves it as well, but Linearith is, again, it's a bit more overkill, so to speak. Linearith is going to, you can see the example here, Linearith operates on variables as well. We don't necessarily need something like that. Okay, so for 1.3, suggesting x plus y is equal to x plus y by ring. All right. Oh, but actually, so our shock was suggesting Linearith for this whole thing by Linearith closes the goal. So you don't actually need to use a high-powered tactic in calc block to close all of this. So good job, Arshak. You totally got that right. Linearith closes this. Let's do it with a calc block though, and that's sort of the practice your problem solving skills. If you're just writing proofs to close your goals, just totally use the tactics and do it in one shot. But okay, yeah. MM's goal was to do it with x plus y is equal to x plus y. Let's run with this and see. So we have by ring. Okay, how should we proceed? Now we have an x plus y on the right-hand side. Any other suggestions? I want to turn this x plus y into something that'll get me a little closer to 2. All right, turn it into x plus 5. All right, how do we do that? By rel, okay. So what symbol should I put here? Do I need equals, greater than equal to, or less than equal to? Less than or equal to. All right. X plus 5. And yep, we'll need to put in the H1 here. Okay, oh. It did like that. Greater? Well, ooh, put it in parentheses. There we go. Yep, and we're getting closer. How about next? How did I type that? I copied it from above. But I think you can also access it with less than equal. Yep, slash LE does the trick as well. Since you have a copy of the code running, you can also put your cursor over there and you can see it's LE, LEQ, and so forth are different ways to get that. All right, so now we have this one. How do I get this and show that this is less than 2? All right, -2 plus -2 5. So do we want a less than or a less than equals? Less than equals. Less than equals, we will do -2 plus, parentheses, -2 plus 5. And I'm just going to make a point. Good solutions and good care to be taken with the way these parentheses work. We've actually found we've run into a lot of frustration when we have like complex equations that have tons of little variables, sorting through substitutions and doing simplification with lots of different operators. Being mindful of where you put parentheses can be really helpful. So this one will be by what tactic? Rel H2. All right, how do we finish this up? I'll suggest we can wrap it. Yes, there we go. Equal, so less than or equal to 2 by norm num. Oh, I missed my colon equals. There we go. All good. Great. Thank you everyone for participating so actively and working through these problems. I will clean it up by taking out this one more with an underscore. Oops, I took out too much. There we go. So if you're finding this fun, I hope you are, go back to Mechanics of Proof, Chapter 1, and work a lot more practice problems. I put this comment, many tactics can solve simple number relationships. I want to delete this whole thing and say this is not actually something helpful or interesting. I was just trying to illustrate some different tactics. One of my students had put these examples together, and I was like, yeah, great, that's a fun idea to show. I can replace, I can run linearith on all of these, for example. But very helpful, important point from Kevin Buzzard is, if you have an overkill, Reed can't even do that one. Like if you have a tactic that is overkill, you shouldn't be doing that. So for in this case, here I have some code from what if you have count heartbeats in this first one, the output message is I get 1142 heartbeats. If you put count heartbeats on the second one, it says use 146 heartbeats. This is nearly 10 times faster to use normnum than to use linearith to show that 9 is greater than 4. So normnum is the better tactic to use in this case. What do heartbeats mean? It's timing. You may have used, if you've ever written Python code, you might have imported the time library and said time start at this line of the code, time end at this line of the code, and tell me how many machine seconds essentially you got from this. And that's a common way that people will use to benchmark the efficiency of different pieces of software. Well, here in Lean, heartbeats is the way that works. And I don't know officially exactly what a heartbeat is, but it's related to the amount of processing that Lean is doing under the hood in order to run and compile these problems. So it says this is the most useful setting for setting sufficient but reasonable limits in this. And you can learn more about heartbeats elsewhere. Not a big scope of the course at this point, but this can be used quickly to show that linearith is much less efficient than normnum. Normnum is the better tactic to use when you're only handling numbers. All right, I hope you're having a good time. We've made it through one chapter of Mechanics of Proof, and if any of this is challenging for you, if you have questions, bring them to Zulip. You can ask them now, and we will continue next week. Next week, we will get to proofs with structure and proofs with structure 2. So this is a lot to cover in 1 week. We'll see how much we pull together. Again, you can go to Mechanics of Proof and see this done a lot more in detail and rigorously, but essentially what these start involving is um, and excuse me, or and exists and for all these kinds of logical operations. So we'll introduce that syntax, what those are, and bring up some illustrations of how these can be relevant and interesting in science and engineering, and talk about the ways that we can try to solve these and teach you about how those work. Thank you.